Okay, let's take a look at an example of applying Green's theorem. Now, it goes both ways. You can turn a thing that looks like this into a thing that looks like that. You can turn a thing that looks like that into a thing that looks like this. But, well, one thing at a time, right? So let's, as our first example problem, take a look at evaluating the line integral over c. So you see which direction we're going, right? From this to that. Okay. Of x squared y dx plus xy dy. Okay, where c is the rectangular curve. It's not very curvy. It's actually very straight. Okay, the curve. We still just say curve in general. Okay, because you can have c be very curvy in general. So rectangular curve. And let's just draw it. Okay, so in the xy plane, I think it'll actually help if I just draw the curve in another color. I think I've got the red in thick here. So it, say starts at the origin, moves along to the right, then moves up, then moves left, then moves down. And so that's the curve. Let's put in information about how that's the x coordinate 2 there, and the y coordinate is 3. So in red here is shown the curve C. Okay. All right, so the question has been stated. Now, if we were to start answering the question, let's note that one method would be to ignore Green's theorem, is to just do something literally as stated. And you'll notice there's really actually, even though it looks like one integral sign, because there's the dx and the dy, there's actually two separate, it's technically the sum of two separate integrals here. That's the way to think of it. So one method would be this, would be to parameterize the four separate line segments right, there's four line segments that make up C. 1, 2, 3, 4. The four, four separate, because you couldn't do this all with one parameterization. So four separate line segments, and then do the sum of separate integrals. And so four separate line segments with technically two separate integrals, you're really going to do a total of 8 integrals if you do it that way. Now, look, none of the integrals are bad. They can all be done, but it's just a lot of work. 8 separate integrals to do. So check this out. Instead, let's note that right there, x squared y is p and xy is q. Let's just write that down. First time around we're doing this, let's just write down. So instead, what we're going to do is by applying Green's theorem, we're going to have p, just matching the notation with what's in the box, is x squared y. Q up in the box for this problem is xy. Then the integral over c of p dx plus q dy. That's what we were asked. Yeah, this is now written this way using capital P and capital Q. And then by applying Green's theorem, this is going to be the double integral over d. So we'll talk about d in just a moment. But just copying from the box up here, so we should have partial derivative of q with respect to x minus partial derivative of p with respect to y dA. Now, what is capital D here? This is the filled in rectangle. This is filled in. Let's just clarify. We better be very clear about this. In fact, if we just draw a picture of it real quick, it's really that rectangle filled in. So there's 2, there's 3 on the x and the y axes. This is a picture shaded in. That's D here. Okay, so then if we really write out what this double integral is going to do, let's go ahead and do this as a dx dy integral. X goes from 0 to 2, y goes from 0 to 3. You don't have to work so hard for the bounds for your integral because it's a rectangle. I mean, if we had a slanted line, we'd certainly have to work a little harder. So, partial derivative of q with respect to x, well, look up here. Partial derivative of q with respect to x is going to be y. And then minus, then we need partial derivative of p with respect to y. So looking at this, we'll have an x squared here. Now, we won't go through, this is a good old double integral. It's the kind of problem that could have been given, I think, on the first day we looked at the previous chapter. So we will skip the steps here and just, I believe in the end, the number you should get is actually 1 for this integral. But the point is that this can be done. Let's do another example. Let's erase the example we just did and look at another example. So let's do this. The line integral over the curve C of x squared y squared dx plus 1/3 x cubed y dy, where C is the triangular curve from 0, 0 to 2, 0 to 0, 4 back to 0, 0. So now the curve has been described in words. So let's draw a picture. I think that makes things a lot easier to deal with anyway. So let's see, there's 2 on the x-axis, there's 4 on the y-axis. Let's draw the picture of the curve in red here. So starting here at the origin, going to 2, 0, traveling this way, from there going to 0, 4, and then, traveling that way, and then going back down from 0, 4 down to 0, 0. Because we are going to need it a little bit later, so let's just go ahead and draw the filled in region. So the curve on the outside, the 3 line segments all together form C, but they end up forming the boundary of a filled in region. So let's just go ahead and draw it, because we know we're gonna apply this new Green's theorem thing. Yeah, there's 4 again. Let's say there's 2, so there's that, and we've got this filled in. And let's just go ahead and mention that an equation for this line is y is equal to 4 minus 2x. Okay, so then the integral over C of, we had x squared y squared dx plus 1/3 x cubed y dy equals, well, let's just point out that this part there, x squared y squared, this is capital P, following the notation up in the Green's theorem box up here. And then this 1/3 x cubed y, that's capital Q. So by applying Green's theorem, this is going to turn into the double integral over the region D. So D is this filled in triangle here. Okay, capital D is the filled in triangle. And then we're going to have here x squared y minus because of right there, 2x squared y. Now, where did these come from? Just following what we see up here, we've got partial derivative of q. This part here is partial derivative of q with respect to x. So you got to look back here, take a derivative with respect to x, and you ought to be getting x squared y. And then this part right there, this is just our computation of the partial derivative of p with respect to y, and y because it just comes from the Green's theorem formula up there. Okay, oh yeah, and a dA. Okay, copying that dA in the box up there. Okay, and then, well, to integrate over this two-dimensional region here, so integral sign, let's leave just a little bit of space, integral sign. Actually, what's in here we can simplify nicely, but just by collecting like terms, it ends up being a negative x squared y. Let's go ahead and set this up as a dy dx integral. So I did that just because the y bounds below start at 0, and then the upper is a function of x, and so that way we didn't even have to be, just to be lazy, we don't have to go solve for x. We just, the upper y value is 4 minus 2x here, and then when we project the x bounds, well, we can see it from the picture, 0 to 2 here. Okay, so this is a nice enough integral. We're not going to do all the steps to computing this integral right here. Could have been like, on the second or maybe third day in the previous chapter. Let's just mention that this should give the value negative 32 over 15 when all is said and done.